Hello everyone, welcome to Power Electronics session 21. In the previous session we discussed SMPS circuits, one of the SMPS circuits, that is buck converter. Now we are going to discuss about other two converters, that's nothing but boost converter and buck boost converter. So first we will discuss boost converter. So boost converter, it is more or less same as the step-up converter, whatever we discussed in case of choppers. Only the difference is capacitor. Capacitor is there, that's like an inductor, and capacitor will act as a filter. Now here, this switch will be there to have like a kind of like if you turn on and all this one, then energy will be stored in inductor, and then that inductor energy will be utilized to supply the load when switch is off and all. So that's where we can actually step up the low voltage to high voltage. Okay, the same, it is almost same as what we discussed in the choppers, but only the difference capacitors. Now look at when the switch is on, what will be the equivalent circuit diagram. Equivalent circuit diagram is nothing but as it is everything, but this inductor is actually getting charged by the source like this, by this switch is actually turned on. At that time we can see that this inductor voltage, this is actually negative voltage, so negative polarities appear here, that's why this diode is reverse biased. But as I told you in other circuit, that means buck converter, this load is always drawing the constant value. That is why, so if you assume previous operation is there, we are taking this equivalent circuit in the middle of operation. In that case, what will happen? This capacitor will supply the energy to the load. So this is the capacitor current is actually positive direction we assumed, but here now this capacitor will supply the energy to this one, which is stored in the previous operation. That's what. Suppose you are actually operating this converter as a first time. In that case, at least like 2 to 3 cycles, this capacitor will not supply the energy enough to the load. Okay, that's the difference we need to understand. But assume we are taking this operation in the middle of that, then obviously what will happen before turning on the switch, earlier we have the capacitor already charged. How this capacitor getting charged we will see later on. But now assuming that capacitor is already charged, in that case this is enough to supply the energy to the load, to maintain this load current constant. That means this capacitor is discharging with the constant load current. That's what we need to remember. Okay, and at the same time this inductor voltage is also important. So in this case inductor voltage VL is nothing but source voltage VDC. In this case this is getting charged, and this inductor voltage is constant because it is a DC. That's why current flowing through the inductor is a linear, because this voltage is constant. That also we need to remember. So here this in this time, like you can see that capacitor current IC is nothing but negative of the load current. Why negative of the load current? We taken this is a positive direction of the capacitor current, but now it is reverse actually, that's why negative, and it is supplying the load current I0. Okay, that's what we need to remember. Next, after some time, that means after energy is transferred to the inductor, we will turn off this switch. Then in that case this source and inductor, it's like acting as a source now, both will supply the energy to the load. So that is a T of duration, that means half duration of this switch. In that case equivalent circuit will be like this. That means the switch is also turn off, then it is acting as an open circuit. Now we can see that inductor voltage is actually reversed compared to the previous one, because the current will be in the same direction. That means charged inductor will discharge in the same direction of the current, but only the difference is polarity will be changed. Now you can see that this is the aiding nature. This is positive already, so positive negative, that means these two are actually aiding nature. Both will combinedly supply the energy to the load. In this duration, this IL is same as the diode current. The diode current will be splitting into two portions. One portion is nothing but whatever the average load current available in this will be flowing through the load, because this capacitor will not actually allow the DC current. That's why load is actually drawing the constant current from ID, and remaining ripple current, that's nothing but AC component, will be flowing through the capacitor. So now in this direction, capacitor current is positive. So that means this capacitor is actually getting charged by this ripple current. That charge is actually utilized to supply the energy to the load during this T on. So that's what I told you. Okay, so now look at here, this load voltage assume constant positive negative, that will be appear across the capacitor because capacitor is connected across the load. So that's why in this loop we can see that the KVL equation, that means source voltage VDC plus temporary source voltage VL equal to the load voltage V0. Okay, that means VDC plus VL equal to V0. From this equation, from this one, what is the VL? So VL is nothing but V0 minus VDC. Okay, so we assume that load voltage is constant and then this is constant. Again the voltage across the inductor is constant, that's why inductor voltage will be linear current, that means it is a ramp. But now this is getting discharged, that's why it will be kind of like changing from max value to minimum value linearly. And capacitor current is actually different now. This is the ripple current will be there, whichever it is there from the ID or inductor current. That ripple current is flowing through this, and the load current is actually constant, that is drawing from the or coming from the inductor current of this one. But one thing you need to remember here, which are the state of the switch, whether the switch S is actually on duration or off duration. You can see that inductor current and source current are same all the time. Okay, but in the buck converter we have seen that inductor current is always like inductor current, average current is always same as the load current. But here average value of the load current is nothing but average value of the source current. Okay, ripple will be there, that ripple is different, but average values I am talking about. So remember this. Now by using these things we are going to draw different waveforms. Okay, so in case of buck converter we discussed like a 4 waveforms only, but here we require 5th waveform, that's nothing but diode current also required. So voltage across the inductor, then inductor current, then diode current, then capacitor current, and finally capacitor voltage. Capacitor voltage is nothing but V0. So you can take this one as a V0 also because both are same. Okay, so that's what. Now as we already discussed during T-on, okay, so during T-on VL is nothing but VDC. So if you take that one, so during on duration of the switch T-on, you can see voltage across the inductor is VDC. Likewise during T-off, you can see T-off voltage across the inductor is V0 minus VDC. So same. Okay, this is V0 minus VDC. Like that, if you turn on and turn off the switch, this will be the inductor voltage. Now during this period, as I told you that during this period inductor is getting charged with constant voltage, that's why this will be linearly increasing like this. That's nothing but assume previous pulses there, it is starting from min to max. But in this duration T off, you can see that inductor is getting discharged with a constant voltage, that's why current will be linear, but it is changing from max to minimum. If you keep on turning off the switch, then inductor current will follow like this. Okay, so this will be the maximum current and this will be the minimum current. Always the inductor current will be changing max to min to max like that. So now if you take the average value of this, it will be exactly in the middle of IL max and IL min. So this is the IL, average value of the inductor current. As I told you, so this you can also take it as this average current will be taken as a average value of the source current. Okay, so this peak to peak ripple is there, there's nothing but difference between IL max and IL min, that is generally called peak to peak ripple. That peak to peak ripple is same as source peak to peak ripple current. Okay, remember that. Now diode current. During on duration of the main switch, diode is in off state, that's why diode current is 0. It is 0. Then when the switch is on, when switch is off, during the time diode is getting charged, getting like turned on by the inductor. So then obviously what will happen? This diode current ID is same as the IL. So that's why whatever the inductor current is there during this period, that portion will be flowing through the diode, same current. It is starting from here and then like this. The same current is flowing through the diode. Now again, if you continue turn on, turn off, then this will follow like this. Now coming to the capacitor current. When switch is on, during the time capacitor is getting discharged with the constant load current. That's why it is supplying to the load with the negative current. That you can take it as a load current only, I0, but it's the negative side. Now when the switch is off and diode is in conduction, during that time this inductor current is same as the diode current. That diode current is splitting into two portions. Constant value is flowing through the load and remaining ripple is flowing through the capacitor. That means if you assume load current is constant in this duration, remaining ripple same like a waveform shape but reduced max value will be flowing through the capacitor. That's why this waveform shape will be same but this value will be reduced. So that's the one. Again minus I0, then ripple, minus I0, ripple will be flowing through the capacitor. Now coming to the capacitor voltage. During this period, capacitor is getting discharged with a constant current. So current is constant, then obviously voltage across the capacitor will follow the linear curve. But during this period, this capacitor is getting discharged. That's why you can see that capacitor voltages keep on reducing. Then again in the off duration, capacitor is getting charged. That's why voltage will be increased, but that voltage will follow the parabolic waveform because this capacitor current is constant. If current is linear, current is linear, then it is like a kind of parabolic shape. So it will be increased like this. Then again same thing will be followed throughout the operation. But now you can see that, so here if you take the average value of this, that is nothing but output voltage or capacitor voltage, V average. That means this output voltage is actually having the ripple peak to peak like this. That means this is a maximum ripple. So if you take this one, so you can see that this is like a max value of the load voltage and this is a min value of this load voltage. You can take like this. So this difference is nothing but max and min difference is nothing but delta VC or delta V0. That's the peak to peak ripple voltage. These are the waveforms we need to know for boost converter. Okay, so now using these waveforms we need to calculate some of the important things what we discussed in case of buck converter. Same way we need to look at here. Okay, so moving on, as I told you, like we need to remember that this is also like a kind of average value of the source current. And we need to remember the difference between max value and min value is nothing but delta IL, peak to peak ripple in the inductor current. Okay, again I'm telling that. So remember delta IL is also same as delta IDC. So that is nothing but peak to peak ripple current in inductor current. Okay, that is nothing but you can take it as a IL max minus IL min. Okay, that's what you need to remember. Okay, so if you want to know like I average is actually like inductor current average value exactly in the middle of these two, means this difference is nothing but IL max by 2, delta IL by 2, and this difference, lower difference is same thing, IL delta IL by 2. So remember that. Similarly, as I told you just now in the previous slide, so this max value and this min value, that means this is the peak value of the output voltage or capacitor voltage, and this is the minimum value of the output voltage or capacitor voltage. So this difference is delta VC, that means peak to peak ripple in the capacitor voltage or output voltage. Remember that. The peak to peak is happening during this time, that is nothing but T on. So in that case, to calculate this one, we require the like a kind of like a area under this curve. Okay, we'll discuss that. This area under this curve is important. Okay, we'll see. Now First thing we discuss about kind of like a delta L we need to calculate, that decides the how much inductance value we require. So how to calculate this delta L? As I told you that inductor voltage VL equal to L into di by dt, but inductor current is following linear, that's why you can take it as a delta IL by delta T. Okay, that means inductor voltage VL equal to L into delta IL by delta T. Okay, change in inductor current by change in time. So that you can take it as a, so what is the during T on or during T off, you can calculate, both will give the same information. But T on, if you look at that, what is the inductor voltage? VDC. So VDC equal to L into delta IL, that is what we need to calculate, divided by delta T. Delta T is nothing but T on. So from this equation, what is the delta IL? Delta IL equal to, from this, VDC into T on. T on, I told you that we can take it as a D times T. So that's why you can say that it is VDC into dt by L. This can also be taken as a VDC into D by FL, because T is nothing but 1 by L. So this is what you need to remember. Okay, so remember, if you are having generally to design the filter, delta L will be given, like we need to design the filter for 2% ripple or 10% ripple or 5% ripple, and duty ratio is given to you, and obviously what is the switching frequency will be given. So once you know all these things, means you can calculate the inductor. Remember, as I told you in case of buck converter, so you can see that inductance value is more and more, then this delta will be lesser and lesser. If you assume infinity, then almost you will have a constant current, no ripple at all. That is the meaning of filter. If you are increasing filter values, then obviously ripple will be keep on reducing. Likewise, if the switching frequency is increased, that means you are actually operating the switches at very high speed, then this ripple also will be reduced. This is the reason we generally operate the SMPS at very high frequency. Okay, remember. And as we already discussed in the buck converter, same thing. So delta IL max is, IL max is nothing but IL average value plus delta IL by 2. Likewise, IL min is IL average value minus this difference, that is nothing but minus delta IL by 2. So that is, but how to calculate the IL here? As I told you already, IL in this case is nothing but average value of the source current. How to calculate the source average current? That's where we need to go for the, it's a power balance equation. So before going to the power balance equation, in case of boost converter, it is same as step up converter. So V average is nothing but VDC divided by 1 minus D, same as what we discussed in case of boost converter, but step up chopper. Okay, same as that. So no difference. You can calculate, if you want calculate, means you can take that area under this curve divided by time period equal to 0, then you will get the same equation. Okay, remember that. Now power balance equation, if you go for power balance equation, means whatever the source is supplying the power is consumed by only load, then in that case what will happen? So VDC into IDC equal to V average into I average. So from this you can take it as a like a V average divided by VDC equal to IDC by I average, that is equal to, you can see that if you take this one here, means remaining is nothing but 1 by 1 minus D. Okay, this is a power balance equation. Okay, so how to calculate the IDC? IDC can be calculated from this using this equation. But how to calculate the I0? If you know the I0, then you can calculate the IDC using this equation. But how to calculate the I0? I0 is nothing but V0 by R. But how to calculate the V0? Using this equation. Once you calculate the V naught, then you can calculate I naught. Once you calculate I naught, you can calculate IDC using this equation. Then that is nothing but IL. So that's the meaning of that. Okay. Then we need to calculate some more things. Then we will move on. So as I told you already in the previous slide, this is the difference between the max value and min value of the capacitor voltage. So delta VC, that is happening during this time, that's nothing but T on. Okay, so this area we need to know that. Okay, as we already discussed in buck converter, it's like a kind of delta VC is nothing but 1 by C integral from T1 to T2 IC dt. So this is nothing but area under the capacitor curve. Okay, area under capacitor curve, capacitor current, you can say area under capacitor current. Okay, during that period when it is happening, max to min, it is happening during this time, that area. So that's why delta VC is nothing but 1 by C, then area under this is the rectangle. What is the area under this one? It is nothing but I naught into T on. So that's what I naught into T on. What is the T on? T on is nothing but dt. Okay, so that's why delta VC is nothing but I naught into D divided by, okay, by FC, because T is nothing but. This also we can take it as a V naught D divided by RFC. So this also you can take it as, because V I naught is nothing but V naught by R. So V naught there, this one is there, then R is there. If you keep on increasing the capacitance value, then this will be reduced. This we won't touch because this is the load requirement. But if you want to decrease the ripple in the voltage or output voltage or capacitor voltage, you can increase any of these things. That's all. Okay, another one thing we need to calculate, that's nothing but critical condition. So what is the critical conduction condition? Critical conduction. Okay, so what is the critical conduction? Critical conduction is nothing but here this inductor current is just touching the zero axis. This is zero axis. Touching the zero axis means just touching that. It is not staying in that. That means to touch this one, IL min should be 0. So that's what we are taking that. IL min is 0. IL min is 0 means, I already told you that in the previous slide. What is IL min? IL min is nothing but, what is that IL min? I average minus delta IL by 2. So that's what. So from this you can say like from this one, IL equal to delta IL by 2. So delta IL by 2. What is the delta IL by 2? It is VDC D by FC. 2 is from here to FC. Sorry, 2FL. Okay, that's what we discussed in the previous slide. And you can take it this one further. Further, if you want to take it, means what is the IL? IL is nothing but IDC. So IDC, what is IDC from the previous slide? Previous slide we discussed already. What is that? So IDC by I average equal to 1 by 1 minus T. This is what we discussed. If you include here, then you can see that. So IDC is nothing but IL. So from that you can say I naught by 1 minus T. So that means here I naught equal to VDC D into 1 minus T, because I naught by 1 minus T, that 1 minus T I am taking this side, divided by 2FL. Okay, so that's the meaning. So you can take it as a mean current. This is what this is a minimum current required to have the critical conduction, that you can take it. Otherwise you can take it for the inductor. Generally we will go for the inductor. L equal to I naught is nothing but I naught, we know that. What is I naught? I naught equal to V naught by R. So if you substitute here, that means L, if you take that, I naught comes here, that means V naught by R comes to the numerator. That means VDC into D into 1 minus D into R divided by, it is 2FL into V naught. We already discussed what is the V naught. V naught is nothing but VDC by 1 minus D, or you can see that. So VDC by V naught is there. What is the VDC by V naught? It's nothing but 1 by, what is that? So if you look at like a kind of like in the previous equation we discussed, okay, so V naught equal to VDC by 1 minus D. Now if you take that VDC by V naught, it's nothing but 1 minus D. So likewise, critical inductance is nothing but VDC by V naught is nothing but 1 minus D. So 1 minus D square into D R by 2FL. This is a condition for critical inductance. As I told you that critical inductance is nothing but inductor. If you select the filter inductance L, which is less than critical inductance, then obviously that conduction will be discontinuous. If the filter inductance which is more than critical inductance, then that conduction will be continuous. So that's what the importance of the critical inductance. Okay, so move on. So these are the things related to boost converter. Okay, next and last circuit in SLPS is nothing but buck boost converter. It's nothing but step down and step up converter. In the same converter we can get both things, both the operations. So this is a circuit diagram for that. Okay, so circuit diagram is nothing but, you can see here, inductor will be connected in the middle of this. So when the switch is on, again inductor is getting charged, nothing but it is connected to the source, and at the time diode is open circuited. It's like acting as a boost converter circuit diagram. When switch is off, then this inductor will supply the energy to the load, that time diode is on. That is nothing but its equivalent circuit is actually same as the buck converter off duration. So likewise you can see when the switch is on, that means this switch is on, it is in conduction. You can see that inductor is connected to the source. But remember one important thing in case of buck boost converter. In case of boost and buck converter, this is the positive polarity of the load and this is the negative polarity of the load. But in case of buck boost converter, because of the inductor arrangement, this is positive terminal, this is negative terminal. That is why load current will be upward direction is positive. Okay, and capacitor current upward direction is positive. So that's why diode is connected in the reverse way. So that is what we need to remember. But in the gate exam, if suppose this is given as a positive, this is given as a negative for buck boost converter, in the formula we will have a negative sign. Okay, that is very important. So now inductor is getting charged during this time, and this capacitor which is already charged in the previous pulse will supply the energy to the load with a constant current. Remember, this circuit is exactly similar what we have in case of boost converter during T-on. Okay, now once you prepare the inductor, so if you turn off this switch, then inductor current will force the diode to be turned on. That's why diode is turned on, and now this inductor will supply the energy to the load. Okay, so during that time this inductor current is splitting into two portions. One is average current is flowing through the load and ripple current is flowing through the capacitor. Again these two will be meeting here, that current, same current is flowing through the diode. That means inductor current will actually same as diode current in this duration. So you can simply assume that when the switch is on, that equivalent circuit will behave like a boost circuit. When the switch is off, equivalent circuit will be same as buck converter during T off. Okay, that's what we need to remember. But here you can simply look at here, during T on, whatever the inductor voltage is there, that's same as source voltage. That means inductor voltage is equal to VDC. When switch is off, now look at that, this voltage is same as the load voltage. Now in this loop, what is that? VL equal to V naught. Okay, so but you can see that capacitor current in this duration IC equal to minus I naught, and during this period IC is nothing but it's a ripple of the ripple of ID. Okay, so that means just DC current, sorry, diode current. So that means the waveforms for this buck boost converter exactly similar to what we discussed for the boost converter, but only the difference is VL is VDC during, sorry, VL is V0 during off duration. Earlier case VL during this period is V0 minus VDC, but now just V0. So that's why you can see same waveforms we are going to take. Okay, so during VDC, then half duration V0, same thing, and it will continue further. Then inductor current during this time it is charging, that's why it is increasing to max value. This time it is decreasing, that's why it is actually reduced and increase reduce like that. We'll have kind of like a min current, max current and average current here. Remember, in case of buck boost converter, average value of the inductor current neither average value of the DC nor average value of the load current. Remember, okay, these are the things. Now diode current, diode is actually open circuited during T on, that's why current is 0, and when T off is there, that means during that time inductor current, same inductor current from here to this one will appear exactly similar. Okay, and same thing will continue. Then capacitor current, as I told you that when the switch is on, during that time energy will be supplied to the inductor, during that time capacitor will supply the energy to the load, that's why it is negative I0. Okay, negative I0, and from this average current is flowing through the load and remaining ripple current is flowing through the capacitor, that's why waveform will be exactly similar but magnitude is reduced. So it will continue similar way. Capacitor voltage also will be same what we discussed in the boost converter, nothing difference. Okay, it will be oscillate about average value of the capacitor voltage, nothing but average value of the capacitor voltage is V0. Okay, these are the waveforms. Same waveforms we will discuss and we will continue for other things. Okay, so here peak to peak ripple will be there, as I told you that this difference max value and min value is nothing but delta IL. So delta IL is IL max minus IL min. Okay, that's what. So during T on nothing is changed with respect to the boost converter, that's why same equation you can take, otherwise you can derive also again, not an issue. So that means VL equal to L into D delta L by delta T. So VL is nothing but during T on it is VDC, you can take VDC equal to L into change in current, that is a delta L divided by change in time, that's nothing but T on. So from this delta IL is nothing but VDC into dt, because Tn is nothing but d into capital T. T can be taken as a F 1 by F, that's why F into L. So it is same as the boost converter, but values will be different depending on the buck boost converter. Okay, it's VDC into d by FL. So that's one. Next one, here we need to calculate max and min values of the inductor current. Remember, maximum value of the inductor current, maximum value of the load current, maximum value of the not load current, maximum value of the source current, maximum value of the switch current, maximum value of the diode current, all are same. Remember, if you look at the circuit diagram, whenever the maximum value of the inductor current is there, you can see that that's flowing through it is happening during T on, that means same current is flowing through the main switches and same current is flowing through the diode when switch is off. Maximum same, capacitor maximum current is also will be there, but that is actually depends on the ripple, but no need to worry about that. That's what I'm telling you. Maximum value of the source current, maximum value of the inductor current, maximum value of the switch current, maximum value of the diode current, all are same. Okay, remember, in all the circuits. So IL max is nothing but, as we discussed, it is IL plus delta IL by 2. IL min is IL minus delta IL by 2. But we calculated delta IL. But how to calculate the IL? In this case, IL is neither equal to average value of the source current or average value of the load current. We need to wait for that, how to calculate this. Okay, wait a minute. Now we can calculate the V average. How to calculate the V average? You can calculate the V average by using one equation, concept, nothing but average value of the inductor voltage is 0 for periodical current. Yes, this inductor current is periodical. You can take the area under this curve divided by time period. What is the area under this curve? You can take it like a VDC into T on. What is the T on? It is nothing but dt. T on is nothing but dt minus. Why minus? This is the negative area. Minus V naught into T off. V naught into T off. T off is nothing but 1 minus d times capital T whole divided by time period T, because this time period is nothing but T on plus T off equal to 0. Now you can see that this T gets cancelled, then VDC into D equal to V naught into 1 minus T, because I'm taking this side, okay, positive. So from this you can see V naught equal to, okay, D by 1 minus D into VDC. Okay, this is the average voltage equation for buck boost converter. But remember, as I told you, that output polarity change means you will have a negative side here. But we taken this way, this one by considering bottom is positive and top is negative of the load. Okay, remember that. So from this, how to take it like a kind of like a power balance equation. Power balance equation is nothing but V average divided by VDC equal to IDC divided by I average. If you take the cross multiplication, you can see that V average into I average is equal to VDC into IDC. That is equal to, from this, V naught by VDC is nothing but D divided by 1 minus T. Okay, so this is what. Okay, this is a relationship between source and load current. But now how to calculate the IL? So if you look at in the previous circuit diagram, inductor current is only splitting into two portions. One portion is actually when switch is on, that's same as the source current. Other portion is like when switch is off, that is same as like a kind of diode current, or maybe like a combination of a ripple and average load current. That's why we can take it here. Average value of the inductor current is actually splitting into two portions. That is nothing but one for source, one for load. So based on that, you can take here source current is nothing but it is happening, it is same as the inductor average current, but during T on. That's why it will be D times IL. Similarly, I naught is average value of the load current is same as the inductor average current during T off. So T off will be taken as a 1 minus D. So that's why it is. So I naught and IDC depends on IL. And now whether it is correct or not, how will you prove that? You can take that average value of IDC by average value of the load current. What is that IDC by I naught equal to? So D times IL divided by 1 minus D times IL. IL gets cancelled, D by 1 minus D. That is the same as this one. So this is the relationship between IL and IDC and IL and I naught. So from this, if you want to calculate IL, then you need to take any one of this. Directly you can take that IL equal to I naught by 1 minus T. That you can use. Okay, so that's what. So we established that we calculated the delta IL, at the same time we established the relation among the average currents. Okay, next we need to discuss about this one. What's that? Delta VC. It is same as the boost converter, but equations will be little different. Concept will be same. So that is happening during this time. That's why we need to take the area under this curve. Okay. So that means delta Vc is 1 by C, area under that curve is nothing but I naught into T on is nothing but dt. So that again you can take it as a V naught d divided by FRC. Okay, because I naught is nothing but V naught by R and T is nothing but 1 by F and C already there. Okay, that's what we need to take it. Okay, that's the delta Vc. Okay, then critical conduction. What's the critical conduction? Critical conduction is nothing but inductor current is just touching the 0 and then increase to max value, then 0 increase to max value, like that. In that case, what is that? As we already discussed, IL min must be 0. IL min is 0 means it is nothing but IL min is nothing but IL minus delta IL by 2. So in that case, IL equal to delta IL by 2. What is the delta IL? That is the VDC into D, that's the like year. Okay, delta, that's as we discussed in the previous slide, VDC into D by FL, 2 year also there, 2 FL. Okay, like that. So what is IL? In the previous slide we discussed IL is nothing but I average by 1 minus D. Okay, so that is equal to, if you look at previous slide, you can see that. Okay, delta IL is nothing but VDC into D by FL, and here IL is nothing but I naught by 1 minus D. So I naught by 1 minus D equal to VDC into D divided by 2 FL. Okay, that you can take it as a VDC into 1 minus D into D by 2 FL. Okay, come on, sorry, this is not the right one, sorry, wait a minute. Okay, so because I missed this one, I naught equal to, okay, VDC into 1 minus D into D by 2FL. So that is the minimum required current for the critical conduction. But most of the times we will show this with the inductance only. Then you can take the inductance L equal to like this, L equal to VDC into 1 minus D into D by 2F, and I naught comes here. I naught is nothing but V naught divided by R. R comes to the numerator. So VDC by V naught in this case is nothing but 1 minus D by D. So 1 minus D by D. If you look at previous slide, you can see that VDC by V naught, that means it is nothing but 1 minus D by D. So if you substitute that, DD gets cancelled, then you will get L critical is, you can say it is 1 minus D square into resistance divided by 2L. Okay, so that's the meaning. So remember, and not necessarily in the GATE exam only discussions will be there with respect to L. It can be there with respect to F or like that and all. Okay. So finally, I would like to discuss about a few things in case of SLBS. Remember how to identify given circuit is a buck converter or boost converter or like a buck boost converter. There is a simple thing and all. If inductance is connected on the load side, so that means when switch is on, main switch is on or off, inductor is always connected to the load side, then it is buck converter. When inductor is connected on source side, That means irrespective of, okay, irrespective of the switch on and off, it is always there on the source side, then it is boost converter. But inductor is connected in the middle of source and load, then it is buck boost. Because most of the people will confuse whether it is a given circuit is buck converter or boost converter, because based on that all the formulas will be changed. That's what I'm telling that. So another thing is, in the buck converter, IL is nothing but average value of the load current. In this case, IL is nothing but average value of the inductor current is nothing but DC average value. In this case, neither of them. That's why I told you IL can be like a I average by 1 minus D or IDC by D. Okay, so like that. So remember, again, V average also you can calculate. That is for the this one, like kind of like a buck converter. We know that V average is equal to D times VDC. So boost converter, it is nothing but V average is equal to VDC by 1 minus D. Okay, and for the buck boost converter, V average is equal to D times VDC by 1 minus D. Okay, but remember, sign conversion will be there from source to load. That is very important for this. Okay, so with this I am stopping for all the theory portion for DC to DC conversion. In the next video we discuss about some of the questions, and with the next video I can say that we are going to complete entire power electronics. Okay, thank you.